Good afternoon. Let us start the new lesson. There are many things we have to cover today as usual, but I think they are relatively simple, especially if you remember a little bit about what you have studied in high school about logarithm and exponential functions. But I will not take it for granted. I will try to go through it carefully, but might be a little bit faster to be able to cover a lot of things. Okay, the first thing we want to talk about is the concept of the inverse functions. So what is the meaning of an inverse function? So you remember when I wanted to introduce you the notion of function in the first lesson, so I told you that you have two sets, let me call the set A and the set B, and then you have some elements in this set, for example, and then you have also another element in this set. And a function is a rule that assigns a unique element from B to each and every one of these elements of A. Yes? For example, and then there is, for example, if I want to do the association, for example, I might say that, okay, this point is assigned to this one, this point is assigned to this, and I can say, for example, this one is assigned to this one. I can also say, for example, let us not make it things complicated, this one to this one, but one thing that is important is that I am not allowed to assign two different elements from the set B to one single element of the set A. So in other words, if I decided to assign this particular element to this element from A, I am not allowed to also assign other elements to the same element. In other words, I am not allowed to draw another arrow from this very single element. Yes? That was the idea of having a function. But nothing prevents me to assign two different elements to the single element. For example, here, I can also, if I want to, I can also assign this element to that one. So what you see here is that I have assigned one single element, one unique element from the set B to each and every one of these elements of the set A. So this diagram, hopefully you understand that it defines a function for you. Is that understandable? And then do you remember this set, if this function is called function f, this set is, what is that set? It is called the domain of the function. But then the collection of the points, so I don't know how to draw it, so let me see that. So the collection, let me take these points out and put them here, for example, to make the drawing simple. The set of all these elements is called the range of the function f, which in principle might be smaller than the codomain set. It might be the case that it will not cover everything. If it covers, there is something that you don't need to know. It's called an onto function or surjective function. But what we want to talk about today, what is important for inverse functions, is the notion of one-to-oneness. One-to-oneness of a function, we call it injectivity. So this word is not used in your course, so this is something that you need to know one-to-one. Okay, so what is the meaning of one-to-one? One-to-one is a notion that prevents this from happening. Okay, so this is a function, but it is not one-to-one, because two distinct elements of the domain are going to the same element. If this happens, it doesn't violate the definition of being a function, but it violates what we are going to introduce as one-to-ones. But why this is important, let me first motivate you why we need this concept. The idea of the inverse function is to actually reverse the arrows. So it means that if you have a function, if I want to talk about the inverse of a function, it means I want to simply reverse the direction of these arrows. Okay? And I hope that you see that if I reverse all these arrows, do you think still I have a diagram of a function or not?
No.
No. Why is that happening? Because if I take this off, and just reverse the direction, okay, then this one particular element will go to two elements. This will happen. And can I call it a function again? No, because this is violating a function. I am not allowed to send one single element of the domain to two distinct elements. So you see, if my goal is to reverse the directions of all arrows, but one thing that I want to keep is the functionality. I want to have this a function back. So if I want to have a function back, I have to prevent this from happening. Otherwise, it might not be a function when I reverse the arrows. Is that right? So this is why we need one-to-oneness. Okay, so if I want to define one-to-oneness, I would say that if I give you a function f, and if I give this function has domain df, I would say that the function f is one-to-one on its domain if this implication holds. It means that if f of x1 turns out to be equal to f of x2, this then implies the equality of x1 and x2. Okay, so I would say that for all x1 and x2 in the domain of f. So do you remember this upside down a means for all. So you see, I give you a function. The function has domain df. I want to introduce you what do I mean when I say this function is one-to-one or injective. It means that equality of f of x1 and f of x2 for any arbitrary pair chosen from the domain implies equality of x1 and x2. If this happens, it means that this function is one-to-one. This is the definition. Or, if you remember, we talked about this. Every conditional statement, do you remember, it is equivalent to what? To its contrapositive, yes? So it means that I can swap these two, but I have to negate the statements. So this is equivalent to write it the other way around. Let me write the negation of this one first. Implies the negation of this one. So it doesn't matter. Sometimes they are two equivalent statements. Sometimes it is easier to use the original definition to show that a function is one-to-one. Sometimes it is easier to use its equivalent. So it doesn't matter, but hopefully you understand what does it mean. For example, if I just go back, so is this function one-to-one? Intuitively you should say no. Why is that? Because, for example, if I choose x1 and x2, x1 and x2 are not equal, it should imply that the images are not equal, but it is not the case because the images are the same, so it means that this function is not one-to-one. So if someone asks why we really need the notion of one-to-oneness, because we want to construct the inverse function. If the original function is not one-to-one, there is no guarantee that when I reverse the arrows, I am ending up with the function. Is that clear, everyone? Okay, so let us go to the first example. Okay, I forgot to talk about what does it mean graphically. So how do you know, if I give you the graph of a function, how do you know that it is one-to-one or not? So for example, let me ask you a question. Do you think that this function is one-to-one? Yes, if you see the graph, why?
It's a horizontal line.
Because every horizontal line intersects the graph at most at one single point. But for example, is this function one-to-one?
No.
No. For example, this value, if this is x1, this is x2, on the picture you see that x1 is not equal to x2. This is clear. But if I ask you what is f of x1, you will tell f of x1 is 0. You will tell me f of x2 is also 0. So even though x1 and x2 are not the same, but the values of the f's at those two points are the same. So this is violating the definition of one-to-oneness. So graphically speaking, what do you think about this one? Is this function one-to-one?
Yes.
Yes or no?
Yes.
Yes or no?
That's not a function.
That's not a function in the first place. So one-to-oneness is an attribute we associated with the notion of a function. This is not a function. Why? Because if I draw a vertical line, it will intersect the graph at more than one point. So this is not even a function. But if you have a function, meaning that every vertical line intersects the graph at most one point, then you can talk about one-to-one-ness of that function. So this is not still a function. Okay, but if I take this off, this is both a function and it is also one-to-one. Yes, it's actually that's the meaning of graph. Okay, so that's a very simple notion. So let us do the examples. Okay, so you can see the examples here. I can write them on the board. Okay. So if this is given in the exam that you are supposed to show that a function is one-to-one. For example, example 1. I have given you a function, f of x is equal to 2x cubed plus 1. A very, very simple example. I am asking, do you think this function is one-to-one or not? So what should I do? First of all, I have to have an idea of the domain of the function, because in the definition of injectivity, one-to-oneness, I need to know somehow what is the domain. So by the domain convention, what is the domain of this function? Domain is the set of all possible values that makes this function meaningful. Do I have any restrictions here? Nothing. So the domain will be R. And then I would say that let x1 and x2 belongs to df, and f of x1 is equal to f of x2. We show that. So we show that what happens? Help me. We show that if f of x1 is equal to f of x2, I show that x1 is also equals to x2. Okay? But that is simple, because when you tell me that f of x1 is equal to f of x2, then it means that 2x1 cubed plus 1 is equal to 2x2 cubed plus 1, and then you see that this one and that one are cancelled. That is the whole point. I want you to understand something. Because the form of the left-hand side matches with the form of the right-hand side, you cannot jump to the conclusion and say that, okay, x1 has to be equal to x2. This is correct, that if x1 and x2 are equal, this holds. But we are interested in the reverse direction. There is no guarantee yet. You have to be careful about this. So ones are cancelled, and then you get this one. And then, so is it allowed to do that? Yes, I can add -1 to both sides. Then I can divide by 2. And then I can take the third root. I am writing it intentionally like this because I want you to understand that you have to respect, not just because the form of the left is equal to the form of the right. You are done, yes? But the third root of x to power 3 is nothing except x1, and that one is x2, so yes, that's the case. If f of x1 is equal to f of x2, I was able to do it legally every step and conclude that x1 is equal to x2. Okay, for example, I haven't written this in the examples, but let us say, for example, if I give you this, and if I want to show that this is indeed one-to-one, what do you do? So you in principle write f of x1 equals to f of x2. F of x1 equals to f of x2. x1 and x2 should be chosen from the domain. It means that there is only one restriction about x1 and x2. They are not supposed to be equal to 1, because then I would be in trouble. x1 and x2 are completely arbitrary, except I know that they are not equal to 1. But if I write f of x1 equals to f of x2, this means that this one, I have seen many students actually believe that because this one is equal to this one, then x1 has to be equal to x2. Okay, so if you just jump to the conclusion and conclude this, that is not the case. You have to really show that this is working. For example, in this case, you can say that if I have a fraction equals to another fraction, there is no guarantee that the numerators are the same and denominators are the same, but it is guaranteed that this one multiplied by that one is equal to this one multiplied by that one. So do you see that you have to follow the exact rules? And then you know that, of course, I can multiply that. This is not in the examples, but I think that's also a good example to see. And then you see that x1, x2, x2, x1 are exactly the same, so I can move it to the other side, then they will cancel out. then I am left with minus x1 on the left, minus x2 on the right. Equality guarantees that now x1 is equal to x2. Okay, so you have to actually show that this is indeed the case, not just because the forms will always be the same, because f is the same function. So if you write f of x1, you get the same expression for x1. F of x2 is the same expression for x2. Equality of them, you should prove that they are indeed the case. That this is indeed the case that x1 is equal to x2. So that is some example. So for example, the next one, I have written example number 2. So of course, if I say this one, do you think that this is a one-to-one function? Okay, if you want to say yes, so some people write like this. This is a scratch paper, I want you to understand. The first thing you do, I'm writing it with blue. So I go to a scratch paper, I try to see if it is working or not, okay? What do? I would write 2x1 to power 2 plus 1 is equal to 2x2 to power 2 plus 1. And then of course I can simplify ones, I get this. Okay, and then I can divide. And then I can take the second root, but you have to be a little bit careful. So when I take the second root, because the second root is an even root, what should I write? I'm not allowed to write x1. I have to write absolute value of x1 equals to absolute value of x2. And some students I have seen that they say that, okay, this does not imply that x1 is equal to x2. It's not very bad, but mathematically speaking, it is not correct. Okay? You have to bring an example to show why this is not possible to go from here to there. Okay, so what I will myself do, because let us assume that we still don't know if this is injective or not, we start to prove this is injective, then everything goes fine up to this point, and then the last step we cannot take, yes? But when we cannot take a step, it means that someone comes in and say that, okay, you couldn't take that step because you have used this rule. Might be there is another solution to this that someone can prove us that yes, in other way, x1 is equal to x2. To make it clear that no, this is not possible, I would say that I will not write this in the exam. When I realize that I am in trouble and I understand what the problem is, then I will bring a counterexample. And the counterexample is extremely simple. I would say that let x1 be 1, for example, and x2 be minus 1. Okay? Then x1 is not equal to x2, but f of x1, I replace x with 1 is 3, and f of x2 is also what? 3. Okay? So this means therefore f of x1 is equal to f of x2, so f is not 1-to-1. Yes? So if you want to prove, it's better to do it like that, but if you think that this is not the case and you want to say no, this is not 1-to-1, try to find a very simple example that x1 and x2 are not the same, but f of x1 and f of x2 are the same. So it shows that the function is not 1-to-1. So that's the logic behind it. Understandable? Okay. There is another theorem. It's very simple. I want to actually ask about that from you first. So, do you think there is any relation between the idea of a strictly increasing or strictly decreasing and being 1-to-1? Because you know that proving that the function is 1-to-1 or not, for these cases were simple. But if the function becomes complicated, using the original the definition becomes harder and harder. If I make a very complicated function for you, and then if you write f of x1 equals to f of x2, there is no guarantee that really we can do the algebra until the very end point and legally to conclude that x1 is equal to x2. So it would be a good idea if I can have an alternative way to understand if a function is 1-to-1 or not. Yes?
I think if it's strictly increasing or decreasing for the entire interval, then it is 1-to-1.
1-to-1. Intuitively, it is very clear. You have a function because what happens if a function is always strictly increasing? Intuitively, it means that if I draw any horizontal line, either will not intersect the graph at all, or if it intersects, it will intersect at one point. Yes, it will, and of course the other way around as well. If I have this continuum, so it shows that if I know that my function is strictly increasing all the time, or strictly decreasing all the time, I can conclude that the function is a one-to-one. Okay, but it is not area. For example, let us consider it for this case. I want to show that for this case, if I know that this is always strictly increasing, the function is one-to-one. So how should I do that? I will pick up 2 points, x1 and x2, that are not equal. I want to use the second definition. If x1 is not equal to x2, for this case, I want to conclude that f of x1 is not equal to f of x2. Because if I can do that, I am just, I am actually showing that the definition of one-to-oneness works. Okay, so but you tell me, if x is not equal to x1, what are the possibilities? Either x1 is less than x2, or x2 is less than x1. Yes? But I am considering this scenario. This scenario is the scenario that f is increasing. So if x1 is less than x2, f is increasing. What can I conclude? Do you remember the definition of increasing function? If x1 is less than x2, and I guarantee you that f is increasing, what can you conclude?
F of x.
F of x1 is also less than,
F of x.
strictly less than x2. And if f of x1 is strictly less than f of x2, can I conclude that they are not equal?
Yes.
Yes. So I am done for this case. And for this case also very simple. So the proof is actually indeed very simple. But why this becomes important? Because we had another criterion for understanding if a function is strictly increasing or not. What was that? So if I ask you in the previous lesson, if I give you a function and I ask you to show that this function is strictly increasing, what was the method to do? Take the derivative. If the derivative is positive, we discussed about this a lot. Yes, we can conclude that the function is strictly increasing. About the zeros we talked also, do you remember? If it is also equal to, if the derivative is greater than or equal to 0, but it is 0 at most in some isolated points, still we can conclude the strict increaseness. Yes? Is that clear? So it means that from now on, if the problem is simple, so you can, for example, do it like this, that's completely okay, but if the function is a little bit more complicated, now you have another alternative, use the notion of derivative. For example, the next example, so I just want you to feel, so for example, the next example, I have shown you this, I have given you this function, f of x is equal to 3x to the power of 5, and then plus 6 to the power of 3, yes, plus 2x minus 3. Okay? So I am asking you to show that this function is one-to-one on its domain. Okay? I want you to feel, oh, I have to, sorry. Yes. So, I want you to feel, if I don't want to use this new idea, and I want to still stick to the original definition, I am a little bit in trouble, yes? Because then you have to write this one, you have to write f of x1 equals to f of x2, okay? So it becomes 3x1 to power 5 plus 3x1 to power 3 plus 2x1 minus 3, and equate it with another one with x2, similar expression with x2. Yes, of course taking 3 out is simple, yes, but you have to, it is not that obvious because we need more algebraic identity to be able to go step by step and finally conclude that x1 is equal to x2. So I want you to see that the original method apparently does not work, or even if it is going to work, we have to be very creative to be able to find the correct way of going from this to x1 equals to x2. For example, probably we need to do some factorization and things which are not simple. But if I want to use this idea, it's a matter of 1 second. You just take the derivative of this function. What is the derivative? It becomes 15 x to power 4 plus 18 x to power 2 plus 2. Yes? And this is strictly positive, do you agree?
Yes.
Because this is non-negative, it's greater than or equal to 0. Because this is even, this is also greater than or equal to 0. So this is non-negative, this is non-negative, but this is strictly positive. So when I add these three numbers, it is definitely strictly greater than 0. So then it means that f is strictly increasing. Then it means that by that theorem, f is 1-to-1. Okay, any questions? Okay, now we want to talk about the inverse function. So you now hopefully understand. Am I allowed to talk about the inverse function of any type of functions? Let us just review. Yes? No. Because if I have this situation and I want to reverse the arrows, then I can reverse the arrows. I get a diagram, but that diagram does not represent a new function because it violates the definition of a function. So if my function is 1-to-1, then I can talk about the inverse of the function, meaning that if I want to reverse the arrows and still generate a function. Is that clear? Okay. So, but can you tell me, if you want to define this as a function, how do you define it? So, how do you define the inverse function? Do you remember? So let me make this diagram a little bit more clear. So for example, let me take this off. And of course there is no way that so let me take this one, and instead of moving x2 to this point, let me move this one to this other point. And of course then I have to increase the range of my function to cover that one as well. Yes? Okay, so now what you see is that I have a function. And do you agree that this function is 1-to-1?
Yes.
Yes. So now I want to define what do I mean by the inverse function. Okay. So I introduce you a new function. If I want to tell you what a function is, I have to tell you two things. I have to tell you what the domain of that function that I am going to define is, and I have to tell you what the rule of that function is, the rule of assignment. Okay, so can you tell me, I just want you to see if you could understand it yourself. So let us say that I want to define a new function g for you, which I want to call it the inverse of f. And the idea is that I want to reverse the arrows. Okay, can you tell me what will be the domain of g?
The range.
The domain of g will be the range of f. So if you give me a function f, which I know is 1-to-1, if I ask you what is the inverse, the first duty is to tell me what the domain of the new inverse function is. According to what we learned, the domain of the function is the range of your original function. Okay? But now can you tell me what happens? So, what I will pick, if I change the arrow, so let me, for example, concentrate here. If I give you one particular x, it is very common that we take x from this side, but it doesn't matter, these are just letters. And I want to send it back. Okay? It goes to an element here, which I want to call it y. But what is the property of y? So I will define it for you like this. I would say that g acts on x. Where is x? X is here in the domain of g, which is the range of f, such that when g acts on x gives you y. Yes? Gives you y. But you have the right to ask, Babak, what y is. Can you tell me what y is?
fx.
Y is that element from the left hand side which is mapped to x. By what? By f itself. Okay, so g of x is y, where y is the unique element in d of f, such that g such that f of y is x. Yes? So it means that whatever f does, g undoes. Yes? F takes me from y to x, g takes x back to y. That's the meaning of inverse function. Yes? Is that clear? So it means that g acts on x, y is equal to y if and only if f acting on y is equal to x. Okay? But this is the meaning of inverse function, but it is not a good notation. Because if you come into the class, you don't know I am talking about the inverse function. When you see g of x equals to y, you cannot connect g to another function f. So it's not a very good notation. If I want to have a better notation, instead of having letter g, which is completely different from the letter f, which is my original function, let me invent a new notation that somehow gives the idea that this function is related to the function f. And that is called f with a -1 on top of that. So instead of symbolizing g to the inverse, we symbolize it by f inverse. And this means that this is the inverse of the function f. So this is what you need to remember. So I would say that f inverse, instead of g from now on, I put f inverse. F inverse of x is equal to y if and only if f of y is equal to x. And then it is important to know that your x, which appears in front of f inverse, belongs of course to its d. So x belongs to the domain of g, which in this case is f inverse, but it is also the range of your original function. Okay, can you immediately talk about what is the range of f inverse? Can I say anything about the range of f inverse in this diagram?
The domain of f.
The domain of f. So, in order to be able to even talk about the inverse function, there is something I have to consider first, one-to-oneness. If that's not one-to-one, no one will ask you about the inverse. Okay? Is that understandable? Is the concept clear? So you understand what the inverse is doing. It undoes whatever f itself does. Yes? It takes you back to the original. Okay, so now let us, for example, of course, it might be a little bit tricky sometimes. I will solve two examples and then there will be two a little bit harder for your exercise lesson you can work on. Okay, so let me see if I have written it down. Okay, so if I want to go to the next example number 4, it's very simple. So show that the function f of x equals to 3x plus 2 is invertible. And by the way, I forgot to say, when a function is invertible, if there is an inverse for it. It means that if it is one-to-one, okay? So show that this function is invertible and determine its inverse. This is the simplest possible example, but that is a good one so that we can understand what is going on. So, you know why this is a little bit problematic? Can you see what part of this calculation, I just want to see if you can see a little bit ahead. What part of this calculation will be a little bit problematic for us? No, one-to-oneness, hopefully, by using the idea of the derivative, we can actually overcome that. But so far, if you remember in the first lesson that I was talking about the notion of a function, finding domain was simple. Finding the range, we didn't even talk about it, especially we just intuitively took it for granted. But calculating the real range might be really problematic. And why this is here important, because as I told you, if you want to define a function, there are two ingredients you have to introduce. The domain, which unfortunately is the range of the original function, and the rule itself. So might be we will be a little bit in trouble, and sometimes we are. So the next two examples that I will skip, You have to be very careful, but I will tell you how to think about them at least. So, for example, here, f of x is 3x plus 2. If I want to solve that example, I want to show that this is indeed invertible, and I want to find its inverse. To show that this is invertible, there are two ways, because this is so simple. You need to show one-to-oneness. Either you can use the original definition, because here it's extremely simple, and you can also use the derivative. Derivative is probably simpler. So if I take the derivative is 3, and it is always positive. So this means that f is strictly increasing. Then it means f is 1-to-1. Then it means that f is invertible. This is very simple. Now my point is to calculate the inverse. So if I want to calculate the inverse, so I have to tell you what is the meaning of how f inverse acts on x. But this x is not in the domain of f inverse, which is the range of the original function. Okay? So, what is the range of the original function? It is not hard to understand, because the graph of this, at least we know, it's a line. So it covers all the set of real numbers. So you know that this is just a real number. Okay? So, this is not the first thing you have to do, because sometimes it might be problematic. But this is technically the way you have to do it first. But now, I want to answer the question mark. I would say that, okay, I am looking for the question mark. I don't know it. So let me call it y. But still, I want to find x. So what does it mean? It means someone gives me x from R, and the person is waiting for me, waiting so that I can answer what is f inverse of x. I call it y, and I try to find that y for that person. How can I find it? That is very simple, at least in the beginning. That is the definition. F inverse of x is equal to y if and only if f of y is x. So this means what? F of y is equal to x. Okay? But f of y is easy to calculate. Why? This is f of x. I want to calculate f of y. So I replace x with y. So what happens? It becomes 3y plus 2 is equal to x. Okay, but do you remember what I was looking for? I was looking for y. This is not a good relation because it tells me x. I need to find y. So okay, I continue to find y. I want to isolate y. So 3y becomes x minus 2, and I divide everything by 3. So y becomes x minus 2 over 3. Yes? And then you have to finally write the answer. So if for this function in the exam, you just write f inverse of x is equal to x minus 2 and end of the problem here, that is completely okay. Why? Because, do you remember what was the domain convention? If you don't write the domain in front of it, so what does it mean? It means the domain is the largest possible largest possible set for which this makes sense. So because this makes sense everywhere, yes, so you really didn't need to write this, because by writing this together with the domain convention, you actually have written everything. Only to give you an idea that sometimes it might be problematic and you have to be very careful. So let me solve one of the problems again. The next one, the first part only. And I want to leave the other parts for you. Please do them. If you have questions, you can ask me or you can ask your TA. Okay, so the next function is f of x equals to square root of x minus 1. I want to see if this function is invertible, and if it is invertible, I want to find its inverse. Okay. Okay, so is this function invertible or not? So you take the derivative, for example. The derivative of this function is the chain rule, so it becomes the derivative of this one, which is 1, divided by 2 square root of x minus 1. and it is always positive. Because the output of a square root, if it is defined, is positive. So this means that f is strictly increasing. So it means that f is 1 to 1. Let me write 1 to 1 for simplicity like this, and then it means that f is invertible. Okay. So do you remember I told you that in principle it matters we know about this. But let us say that if we are not careful enough and don't care about that, what will happen? Okay, so let us for the time being don't do it in a very correct way. So what you do, you would say that, okay, someone gives me an x, okay, but this x should already be in the range of f. Okay, so let us say that you don't care about these details. Someone gives you an x, and then you want to see how this looks like, yes? You want to know this. Okay, this means that instead of this question mark, for example, you can choose y, and then f inverse of x is y, it means f of y is equal to x. But if I ask you what is f of y, it will tell me it is a square root of y minus 1 is equal to x. This is not bad, but this is not exactly what I want, because I want to know what y is. This gives me what x is. Okay, so you already see this, that is it possible? So for example, you might, if you are not careful and jump to the conclusion that this is the case, do you agree with this step 100%?
No.
Because even if x is negative and you are careless, when you raise it to power 2 it becomes positive and you get something, which in this case is not wrong. For example, if it is minus 2, if I ask you what is y, I have seen some students raise it to power 2 and it becomes 4, and then they move this one to the other side and then they say 5. But 5 is wrong, yes, because if I put 5 back, it becomes 4, square root of 4 is 2, not minus 2. So this root, I don't know if you have heard about it or not, is a false root. Okay? And this is the reason that I am not simplifying the equation in an equivalent way. I can go in this direction, but it is also important to be able to go backward. Okay? So in principle, I have to put this arrow double-sided. This arrow is double-sided if and only if x is non-negative. So it's already an indication that x cannot be any number that you like. Okay, so if you are careful, you know that x should be greater than or equal to 0. But let us continue. If I continue, y becomes x squared plus 1. Okay, and then you might write this only in the exam. If you write just this one in the exam, I hope that you agree this is not correct. Why? Because by the domain convention, people will think that you mean this as the rule, and what is, if I give you this function without, if I give it a name g and write it x squared plus 1, and I ask you what the domain is, what do you say?
All real numbers.
All real numbers. But it is not the case, because x cannot be any number that you like. X should be non-negative. So in that case, you have to write this, and you also have to write the domain of f inverse. The domain of f inverse is 0 to infinity. Okay? So you see, in the previous case, if I was careless, accidentally it was correct. But in this case, if I am careless and just write this one, I will lose the points because I should also specify the domain. I hope that you understand what I mean. Okay? So for example, something that might be also useful, there is a remark I forgot to talk about, how the graph of a function and its inverse are related. Can you imagine? For example, if I give you a function, f, is this function 1 to 1?
Yes.
Yes. But if I ask you to draw the graph of the inverse of the function, can you tell, how can you visualize what will be the graph of the inverse? Because that's also extremely important to know about.
It could be like mirror image in the...
With respect?
Reflection of,
With
reflection of it will be reflected on the line y equal to x.
X.
Yes.
Yes, why is that? Because you see that what we are doing here We are replacing y and x. So the graph of f will be mapped to the graph of f minus 1 if I replace x and y. And you know that if I want to replace x and y, this line y equals to x. So if this is f, f inverse would be somehow something like that, yes? Something like that. They will be symmetric. I cannot draw it exactly, but it means that if this is f inverse. For example, one thing you can see, if f is invertible, what can I say about f inverse? It's also invertible. And what is its inverse, according to this image, is f. So it means that somehow f inverse of inverse is equal to f. So if f is invertible, f inverse is also invertible, and its inverse is the original f. Okay? So for example here, so this is good to know, especially in the exam, especially if the function is not that complicated. Can you draw the graph of this function? If you remember something about this, it's not very hard. You can convince yourself that if this is 1, the graph starts like that. Okay? And of course, okay, it's a very bad place to draw here. So let me clean this. For example, if I have given you this function, if you are good in drawing these simple graphs, so the graph of y equals to square root of x minus 1 is this graph. Because I remember square root of x, which starts from here, the square root of x minus 1 will be shifted 1 unit to the right. Okay? But then what happens for this line? This is y equals to x. I hope that you can somehow see, if I find a mirror image of this with respect to this line, it will go like this. Yes? But again, you can immediately see that if you don't write this, and I ask you to draw a graph of this function, that blue one is not the graph of this function. The graph of this function will be like this. Okay? Which is wrong. So you see that this is a have to. You have to put it there, otherwise this answer is not correct. But this is always correct. So if you can draw the graph of a function and then reflect it in y equals to x, what you get is the graph of the inverse function, and it's always reliable and works. And from there, might be you can see that if you write this, this is wrong, because then it means that the domain of the blue curve should be the whole R, which is not actually the case. It goes from 0 to infinity. Understandable or not? Are you confused or not? Yes?
Can you prove that its inverse is strictly increasing?
Yes.
Prove that the normal function
Yes.
is strictly
Yes,
increasing?
yes. Yeah, that's correct. Okay. So now, let me actually go through them. So these are the things it's good. So I mean, it's good to solve part 2 and part 3 yourself. Let us go immediately to this remark. This is something that actually we talked about. The domain of f inverse is the range of the original function and vice versa. I hope that you can also agree with this relation, yes? So, can you tell me that if I have f acting on x, it gives me a number, and then I will take this number, whatever it is, I apply f inverse on it. What do you think it will give me?
X.
X, yes? But I can write it the other way around. If f inverse act on 1x, it gives me something, and then I apply f on it. What do you think it will give me? X again. Because f inverse, actually they are opposite to one another. But there is a difference here. Is this x the same x here?
Depends.
No, usually no. This x, f acts first. So x should be in the domain of f, which is of course the range of f inverse. Okay? But here f inverse is going to act first. So x should be in domain of what? In domain of f inverse, which is indeed the range of f. But if you correct the set that you are taking x from, both of them are equal to x. Is that clear? Okay. Okay, the other ones I have told you already. F inverse inverse is f of x, and the graph of f inverse is the reflection of the graph of f in the line y equals to x. And the next one is also an exam question. It is always good to work on these, and then if you have problems you can ask Glenn. Okay, the last thing about this we need to know is the derivative of the inverse function. Okay, so the derivative of the inverse function. I want to give you an idea because in this module they are not emphasizing on this part. We need it because it is in the module, and I want you to know it, and then we will continue. Okay, I will give you only one example. I haven't seen any examples in the workshop problems using this, but in the workshop PDF file it was written, you need to know it, okay? And I want to start from something simple, okay? So here, if I give you f inverse of f of x equals to x, we had it before, and this is true if x belongs to the domain of f. Okay, so now I want you to help me to differentiate this for x. Forget about the idea if differentiability is correct or not. Pretend that everything is good and it is possible to differentiate. I want you to differentiate both sides with respect to x. So how should we do that? So I will do it like this. I would write it as f inverse f of x, because if this one is equal to x for every x here, then I would say that the derivative of the left-hand side, with respect to x is equal to the derivative of the right-hand side with respect to x. The right-hand side is simple. What is the answer?
1.
1. But I'm waiting for you a little bit. Can you just do it for me? Because it needs something from the previous lesson.
We use the chain rule.
It's the chain rule. Do you remember what was the chain rule? If you have forgotten, I told you f after g x prime. You can flip the prime here,
F prime of gx.
but the price you have to pay is to multiply by the derivative of the inner function. So this one is not f after g, it is f inverse after f. Okay? So if I want to do it, I have to use this. So I can flip the derivative here, but because writing like this is a little bit confusing, so if you don't mind, let me prepare brackets. I flip this here, and I write this down, but the price I have to pay by flipping this here, I have to multiply it by the derivative of the inner function. Is that right?
Yes.
But now, if f prime of x turns out not to be 0, what I can do, I can divide everything by f prime of x. So this will be f inverse prime calculated at fx is equal to 1 over f prime of x. Okay? This is the formula given in the book, and I have written it for you. But this condition should be satisfied. But let me write it usually, because usually if you have a function f of x, if I ask you what is the derivative, you are used to writing at f prime of x. So what you are used to is to put an x there. But here this is not x, this is f of x. Okay, so let me give it a name. So I would say let f of x be equal to y. And then what happens to this notation? This becomes f inverse prime of y equals to 1 over f prime of x. I write f prime and I want to wait for you. What can I write in the pair of brackets? Because you see, a formula is, in mathematics, a formula is useful, that if the left-hand side is in terms of one variable x, the right-hand side should also be written in terms of the same variable x. Okay? So here I decided to change from the variable x to variable y. So in principle, I should also adopt the right-hand side in a way that's also in terms of y.
F inverse y.
It should be, because when you say f of x is y, people can immediately understand that x is what? F inverse of y. So I would write it here. Okay? So this is a good formula. I haven't written it down. Might be I will add it for you later as a remark. That is the main theorem. This is in this way, but I would prefer to write it in that way. So if I ask you where y is from, where is y from?
The range of that.
Y is f of x, so it is in the range of f, which is in the domain of f inverse. So y belongs to the domain of f inverse. Yes, and there is one condition, that f prime of x is not equal to 0. Yes. So, and then it means that f prime of f inverse y is not equal to 0. So you see, what does it mean? It means that when you want to calculate the derivative of f inverse at a point, the derivative of f inverse is the inverse of the derivative. Because when you say 1 over f prime, it means the inverse of the derivative. So the derivative of f inverse is not very hard to remember, is the inverse of the derivative. But if it is calculated at y, you shouldn't calculate it at y, you should calculate it as at f inverse of y. So that's the only thing. So if I want to remember it, very roughly speaking, I can say that this is equal to 1 over f prime. The derivative of f inverse is 1 over f prime, the inverse of derivative. But as soon as I put one y here, I am not allowed to put the same y here. What should I put here? I should write f inverse of y there. Okay, any way that you are comfortable to remember the formula. Okay? Okay, so now let us go to the next example. Oh, I did a lot, yes. So I forgot to stop. So let us stop, have a break here. Thank you.